physics video lecture, Physics 105B video lecture 7. So what were we doing last time? Symmetries and conservation laws. So Lagrangian mechanics, put down some of these terms here. So we're working on Lagrangian mechanics. And follows from a variational principle. Variational principle gives us the equations of motion. And what I'm writing down here is already using the generalized coordinates. So we get the equations of motion. L is a function of the coordinates, their time derivatives, and the time in general. And we had already made a couple of discoveries. So we had conservation of energy. Well, actually, let's write down here, we had discovered cyclic coordinates. Very important. So if L, and the way I'm going to write this, if L does not explicitly contain some particular coordinate, then the corresponding generalized momentum is conserved. Then dl dqi dot, which is the corresponding generalized momentum, is conserved, is constant. Okay. Very important because these cyclic coordinates really express the symmetry of the system. So what we had found right away, because we had kind of inherited it from our variational calculus, was that quantity that turned out to be the energy. So that was conserved when there's no explicit time. Well, time's not exactly a coordinate, but the principle still holds. L is not explicitly a function of time. Then this expression, dl qi dot minus L E equals constant. And in fact, even though last time I showed that under certain circumstances, a certain type of Lagrangian, this was just t plus u. In general, you actually go back to this expression here and construct it to find out what is conserved, because not every Lagrangian has to look like this, just most of them. Okay? Not everyone has to look like this, in which case, if you want to find that conserved quantity, you go back to this expression and construct it. Okay, but L not explicitly depending upon time is an expression of homogeneity of time. Means in an inertial system, time is the same now as it was a moment ago, and as it will be a moment from now. Okay. Time flows uniformly and so forth. Of course, it has to be an inertial system. So we have that conservation law, and what we're going to find now is that the other major conservation laws, linear momentum and angular momentum, also follow just based on a symmetry principle. So this is very important. So the whole title here is Symmetries and Conservation Laws. Symmetries and Conservation Laws. I had given a couple examples last time how it works with cyclic coordinates. So now we're going to turn the argument around, or make it more general. So symmetries and conservation laws. The first one that we're going to do is space is homogeneous. That means if I have an experiment and I just shift the entire apparatus, the physics should not change. Formally, if I have a coordinate system and I shift the entire coordinate system infinitesimally, the physics should not change. Okay? So space is homogeneous, and we say therefore an infinitesimal displacement should leave the physics unchanged. So what we're going to do is this infinitesimal displacement, this is going to be a vector epsilon, and what we can now say is r sub I is displaced to r sub I plus epsilon. Okay. But then if you take the derivative, so this is your old coordinate, this is your new coordinate. You know, I could do a tilde here as well. I'm just going to use that there. Old coordinate, new coordinate. Then you have r sub I dot is left unchanged. Velocities are left unchanged because it's just an infinitesimal displacement. This epsilon is common to all of the coordinate displacements. Time derivative gets rid of the constant epsilon. Okay. What we do is look at the Lagrangian L sub epsilon is equal to L when epsilon is equal to 0, plus now we do a linear expansion. So we can say plus the sum of dl dr sub I dot dr sub I plus the sum of dl dr sub I dot dotted in dr sub I dot. So that would be the linear expansion. And what we're going to require is that this entire part be 0 equals 0 because the physics after the displacement has to be the same as the physics before the displacement. So this change here has to be 0. Because we've required that physics remain unchanged. Okay. So now we're going to work on this thing here. So L sub epsilon is really equal to the original L. This infinitesimal displacement, the effect of that leaves the physics unchanged. Okay, so first of all, the dri dot was 0 because of this here. i.e. dri dot is equal to 0. This one here we could have said dri is equal to epsilon. Okay, the difference in those two, infinitesimal displacement. So this kills this entire sum here, and this sum here. So now, sum over dl dri dotted into epsilon is equal to 0. I equals 1 to n. So what are we going to do with this? Now there are two things. First of all, we have the other half of the Euler-Lagrange equation. So I'm just going to use this section of board. Now, we have, I'm going to do things at once. The epsilon is constant, so I can pull it out, and then I have the sum over d dt dl dri dot is equal to 0. The next thing, this epsilon is arbitrary, so what's in parentheses itself has to vanish. Okay. It's kind of like that fundamental theorem that we talked about in variational calculus, same type of argument, equals 0, comma, because epsilon is arbitrary. Good. And now, I'm gonna, well, let's go ahead and give a little more room here. Having this definition here is not bad. Okay. So now I can do two things. I've called this thing 0, and I can pull the time derivative out. So now we can say, continuing that thought, and the time derivative of the sum of BL dr sub I dot is equal to 0. And you can see now that the sum of all of these vanishes, but those are not only the generalized momenta, in this case they are the linear momenta because we're using Cartesian coordinates. And the n equals total linear momentum is conserved. So you see the conservation of linear momentum also comes from a symmetry with respect to infinitesimal translations. So this is conservation of linear momentum. Or you could say homogeneity of space implies conservation of linear momentum. So let's write that down just so we have it here. Implies conservation of linear momentum. Here we go. Linear momentum. Good, so that's the symmetry, and there's the conservation law. Now, we already saw that in terms of the cyclic coordinates, so I may just bring that example in. So just as the example, the explicit example, explicitly L equals 1/2 m x dot squared plus y dot squared plus z dot squared minus mgz. Remember, that was the projectile motion Lagrangian. It had two cyclic coordinates. P sub x and P sub y were conserved. Okay. And of course, you could do a translation anywhere in x and y. Okay. Without change, and that's why those components were conserved. Okay, you could just do a translation in the x and y coordinate. And in fact, it wouldn't even have to be infinitesimal. You could do a major one. You'd have the same argument. So then P sub x and P sub y are conserved. Okay, so let's do the next one. See if we can fit it on the board this time. Well, I'll get it started right here since I've got the room. So the next symmetry is that space is isotropic. Again, all of these examples only in an inertial system. Isotropic means it's independent of the direction. So if I point my experiment here versus pointing it there versus pointing it there, it's not going to change the physics. Of course, if you're in a non-inertial system, it certainly does change the physics. Just imagine you're on a rotating turntable. Okay? So you have to be an inertial system, in an inertial system. And so space is isotropic. So we say an infinitesimal rotation should leave the system and its physics unchanged. So infinitesimal rotation leaves the physics, and therefore now I'm just going to go ahead and say leaves L unchanged. Leaves the Lagrangian unchanged. Because if the Lagrangian is unchanged, okay, then the equations of motion are the same. That's the expression for the physics of C unchanged. Good. Infinitesimal rotation. Well, what is an infinitesimal rotation? Imagine you have a vector here. We're going to transform this one that's sticking out. This is R sub I. And this vector here is a d phi. It's an infinitesimal rotation vector. And what it's going to do is produce, some infinitesimal rotation around that axis. So it's the cross product that's going to do it. So we have dr is equal to d phi cross r. So you recognize the cross product. This infinitesimal rotation would be somewhat into the board. You can draw it if you want, right? Cross d phi into r sub I, you get something going into the board. So d phi cross r, we'll put a subscript on each one. That's the infinitesimal rotation. And dr sub I dot is the transformation of the velocity vector, so it's also d phi cross r sub I dot. So that's the infinitesimal rotation. We'll block that in so that we can stare at it. And then send this up here. Now this one's pretty interesting as well. Actually, when we do rigid body motion later in the semester, we'll come back to a lot more of this formalism. Right now we're just using cross product to produce a rotation. Good, here we go. So we're going to leave L unchanged. This time I'm going to label our L phi equals the original L plus the first linear terms in an expansion. So dl dr sub I dotted into dr sub I plus the sum of dl r sub I dot dotted into dr sub I dot. And again, we're going to require, right, based on this requiring that, we're saying space is isotropic, the infinitesimal rotation must leave L unchanged. So when we do this expansion, this first little change in the Lagrangian has to vanish. Okay, we're requiring that based on the isotropy of space. So this whole thing is going to be 0. And now we have to make our substitutions. So we have sum over dl dri dotted into d phi cross r sub I. And then we'll have the sum over dl dr sub I dot dotted into d phi cross r sub I dot. So these two have to vanish. And now, okay, we have to we have to get that d phi out front the way we had the epsilon out front. So we're going to use A dot B cross C, which can be, we can cycle these through. So that's equal to C dot A cross B is equal to B dot C cross A. We know that as an identity volume of the parallelepiped, so that's why you can cycle that through and retain the correct sign convention. If we do that here, we end up with d phi dot R cross dl dr. And here we end up with d phi dot R cross, and now, yeah, dl dr I dot. Okay, so we just cycled through twice, that's nice. And we have, again, the Euler-Lagrange equation. So this, I'm going to do two things now. First of all, the d phi is common to all of them, so I can bring it outside the sum. And then under one sum, these all have subscripts, I'm going to have R sub I cross, and I'll use the Euler-Lagrange equation. This is a very common move, right? This is the other side of the Euler-Lagrange equation. And then I'll have R sub I cross dl dr sub I dot. Equals d phi dotted into. Now this is a product rule. Missed the dot here. Dot and dot and vector. This is a product rule. I'm actually doing two steps in one. Let's write out what the product rule is. R sub I cross dl dr sub I dot. I equals 1 to n. So yeah, let me just point at this stuff for a moment. D phi was common, so I pulled it out of the sum. Now you can recognize this product rule. I get an R dot crossed into this, or I'll get an R crossed into the time derivative of that. And we're going to complete the argument. This was arbitrary, therefore this whole thing vanishes, equals 0, because d phi arbitrary. And if this whole thing vanishes, this is fantastic, then the sum is conserved. And I'll do one more thing. This is the linear momentum in Cartesian coordinates. A generalized momentum, but in Cartesian coordinates, a linear momentum. So what we're finding is sum over R sub I cross P sub I is conserved. Yeah, so this was how we get the conservation of angular momentum. Conservation of angular momentum, and I should say conservation of total angular momentum. For all of these situations, we were actually looking at an isolated system in measureless space. Okay, we've got an isolated system, and yeah. So we could have also put, for all of these three, actually the energy, the independence in time on the energy meant the system's isolated. The other two cases also isolated systems. So this is conservation of angular momentum. Conservation conservation of angular momentum. So we're going to use these. We of course had these conservation laws before, but we have them at a much deeper level there in terms of when they hold and when they don't hold. Good. Good. I have an actually important example. Let's see how we're doing time-wise here. We've got nothing but time. Okay. So, symmetries and conservation laws. We had these, got to reiterate, we had them before with Newtonian mechanics. We now have a better sense of what they mean. I want to come back to some problems that we know and just discuss them a little more. And we'll really see the importance of cyclic coordinates now, because cyclic coordinates are explicitly the expression of a symmetry. So I'll write here more on, more on cyclic coordinates and symmetry. Suppose we're looking at our central force problem that we spent so much time on last semester. The central force, it had a number of steps till we finally obtained the energy expression. So I want to write down the central force Lagrangian. So L equals T minus U. So central force, point mass in a central potential. And we know if it's a two-body problem, then that mass M is actually the reduced mass. Central potential. But that makes no difference. Okay. So what would we have here? We would have L equals 1/2 M R dot squared minus U of R for starters. That would be kinetic energy minus potential energy. Now suppose we're in free space. Okay, we're in free space. We know, after all, our conservation laws put us into two space, right? Conservation of angular momentum put us into plane, and then we use plane polar coordinates. But suppose we're just starting from scratch here, point in free space. R is the vector x, y, z. And we even know our potential energy. So L is 1/2, I'm doing Cartesian coordinates, M x dot squared plus y dot squared plus z dot squared minus negative alpha, because, okay, central force problem, Kepler problem. Remember, negative alpha over R, but R would be x squared plus y squared plus z squared. Okay, I may have made this point last semester as well. You're never going to solve the problem like this. Okay. It's going to be too complicated. You're welcome to write the Euler-Lagrange equations out. They will be true because all of these coordinates are independent, so we're not violating the independence there. But this is not going to do the trick. You actually want to make use of a symmetry here and a conservation law. So if you make use of the symmetry with respect to infinitesimal rotations, you get the conservation of angular momentum. You get the motion in a plane. Okay. And so suppose you have the motion in a plane. So, or if motion in the plane but you still insist on using Cartesian coordinates, then you're down to this. X dot squared, y dot squared equals, not equals, minus negative alpha over root x squared plus y squared. You're still not going to get it. Okay. Your equations are going to be two coupled. Okay. So to really make full use of the symmetry of the isotropy of space, you have to let that symmetry be reflected in your coordinate system if you're actually going to practically solve this problem. So let me just go up to here. The full utilization of the symmetry isotropy of space leads to this Lagrangian m r dot squared r squared phi dot squared minus alpha over r. This Lagrangian has a cyclic coordinate. And if you have the cyclic coordinate, you get explicitly the conserved angular momentum. You're not seeing any conserved angular momentum in here, and you're not going to, okay? You explicitly see it, which has phi, it's cyclic, L equals m r squared phi dot is constant. Triple exclamation point. So this is the point at which you can actually solve. We can solve the problem. So the symmetries, the conservation laws, but then the cyclic coordinates, which are the explicit reflection of that, are absolutely important in solving anything. Later on in Hamiltonian mechanics, when you take it through in grad school again, you're finding techniques in which you can actually make all of your coordinates cyclic. Of course, all the work is then involved in making them all cyclic, okay? Because then you can solve, in principle, you can solve the problem. Okay, so that's what I wanted to say here. I've taken us back to our central force problem. We looked at this expression 100 times with a plus sign when it was the energy. Now it's Lagrangian or Lagrangian, Euler-Lagrange equations of motion for this thing, and then you're on your way in analyzing it. And the fact that we solved it using the energy is interesting in its own right, because the energy is also present in the Lagrangian formalism. So if you were to solve this problem, use the Lagrangian formalism, you'd go to the energy and you'd be right back where we were when we solved it last semester. Okay, I think that's a good place to stop. Is it really a good place to stop? 33 minutes. I have one more topic. One more topic I'll put up. The theme of the symmetries and conservation laws section could also be, how much can you learn about a system without actually solving it? And there are some good applications in that. Well, the things you can learn are the conservation laws. And the point here was, even if you write this down, the conservation law isn't just staring you in the face. So, but the analysis of the Lagrangian system can get you to the conservation laws. So that's one thing you can learn. And there's one more thing called the gauge transformation. And it also involves this Lagrangian formalism. I'll just refer to this as a theorem and show it. It is the following. Suppose you have a Lagrangian, and I'm going to name this L tilde. So L tilde is my Lagrangian plus the complete time derivative of any function of the coordinates and the time. Okay. Any function whatsoever of the coordinates and the time. And L is going to be L of Q, Q dot, and T. Okay. All the coordinates, all the generalized velocity of the time. So here's what the theorem says. You can add any complete time derivative of any function of the coordinates and time, and it will leave the equations of motion unchanged. Leaves the equations of motion unchanged. And this means it's sometimes possible to add or subtract a complete time derivative from the Lagrangian and put it in a more convenient form. And what you know is that if you are able to show that your new Lagrangian and your old one are just differed simply by a complete time derivative, then you can declare them to be equivalent. You can know that they're equivalent. Okay. So how do we prove that? There are two ways to prove it. You can actually go through this calculation. If you do it meticulously, it's kind of long. You can just explicitly show that all of these terms here, when you apply the Euler-Lagrange operator to them, they'll all vanish, they'll all sum up to zero. The big raft of them will sum up to zero. The other proof comes out of the variational principle. So we have the variation T1 to T2 of L tilde dt equal to the variation of T2 L plus d dt f of q and t equals the variation L dt plus the variation of what? Now if we integrate this with respect to time and fixed boundaries, we have f of q T2 minus f q of T1 square bracket. And at the level of the variational principle, this is just a constant here, and therefore variation of constant is trivially zero. So what that means is that this and this are equivalent, giving zero. So the equations of motion that come out of this variational principle and this one are also the same. So that's a short proof. It's kind of nice. Makes it worth studying the variational calculus so you don't have to do all these calculations by hand, so to speak. Okay, so that's one more thing in our repertoire. There is a trivial example that we'll start with. F of Q and T equals C. D dt of F equals 0. This trivial example is actually what we've learned in the past about adding an arbitrary constant to a potential energy, which we know we can do. We can add an arbitrary constant to a potential energy and it leaves the physics unchanged. Here adding a constant Oh, not so fast. This was c times t, and that was c. Okay. So arbitrary constant times time, its complete time derivative is just a constant. We can certainly add a constant to the Lagrangian because it'll be differentiated away. So that's something we already knew from Newtonian physics, as is the case in Newtonian mechanics. Okay. There are some more interesting ones that we could talk about later, but this is the basic one, proof of concept. Okay, good. We'll call it a day. This was the 7th video lecture. See you guys next time.